Yeah, the first thing about particle is the one of the reason for which when you have an unstable nucleus. A stable nucleus can decay to form stable nucleus. That's the purpose of a nuclear being decayed is to become stable. So become that is stability that matters. So when you going to A2, are you going to do A2 later?
Yes, sir.
Are you going to write A2 exam?
Yes, sir.
Okay, you understand it better when you talk about when you go to A2, what you call stability, what you call binding energy per nucleus. So that's another aspect. Now we have things J.J. Thompson and Rutherford. So J.J. Thompson is saying that if you have, for instance, you have, let me see, if you have, okay, I will not say this. This is okay. For instance, you have, let's say you have a target, you incident another particle toward this. There are three possibilities here when it gets here. Number one, it can pass through. At the same time, it can get reflected back. At the same time, it can pass through space like this undeviated. At the same time, it can bend, deflect like this. So that's what the Rutherford is saying. But they would, J. Thompson is saying that it is only one possibility. That is only one thing that is possible to pass through. But Rutherford now went further to discover that no, there are three possibilities. And those are the three things we will consider in this particular topic. So that's what we have in this story, sir. Don't let me waste time on it. That's not the major something. Still the same thing here, the story. You can go through. I know. So go through. This is where the major point starts from. The option one, that is, okay, some get deflected, some get reflected, and while some can pass through undeflected. So what can we say about the three? You have a solid something nucleus here. You incident a upper particle toward it. And for it to be reflected back here, it means that this nucleus is more heavier than the nucleus of the upper particle. Yeah, it's more heavier because that means it's able to when it strike this particular object nucleus, then it will reflect back. But what can we say about the one that actually bends through deflected? That means they are far away from the nucleus. Because if actually if they are far away, if they are too close to the nucleus, they will also have what reflected, reflected back, deflected back. And this particular one too means that oh, too far away. So that means the one that passes through is saying that he's seeing the nucleus as an empty space. That is an empty space. It does not really have mass. That's what this one is saying. Seeing the nucleus as an empty space. This particular one gets deflected. Is seeing the nucleus at the same charge. That means so I cannot come towards you. I have to be reflected. So I have to move away. That means we have the same charge. That means the redundant God repulsion occurs. That's what this two is saying. He's saying that that's what he's saying here. Excuse me. Now, the one that actually gets deflected can now go greater than 90 degrees. That's the language. He's saying the nucleus that is nucleus is heavier than the one coming here. These are the three possibilities. So what do we need here? I've summarized what we need to answer question here. So let's go. So are you listening?
Yes, sir.
Okay, fine. Now, you see now, these are the things I put on that note here. For most of the other particles that were the particles that were deviated, that were undeviated, that is the one that passes through. So they were undeviated because the other particles are more massive than electron. Yeah, yeah, of course. Now look at it now. This upper
Yes.
particle, this electron, that means it's able to pass through. That's an substance able to pass through. That means it's more massive than the electron. It's heavier than this. Then it's able to strike and also pass. It's able to strike and pass through. Now, the major thing now is now say, what do you need here? When you say the most of the parts undefeated, this is what you need here. It suggests that most of an hour is an empty space. That's the answer to the question because that's how the question will ask you. So what can you bring out? What does it suggest? What does it mean when you say this? This is the point that you need. For the particles that were deviated, they were deviated because of the electrostatic force of repulsion between the charge of the particles and the positive or nucleus of atom. So they repel each other. Now, the major thing you need there, you don't need really, that's what you need. The major thing you need there, that's not really even the major thing here because they don't use to ask about this particular one. So the part is very close to the nucleus. Yeah, that is why it's able to reflect. to actually to deflect. That means they repel each other. They have the same force, the same charge rather. So of course they will repel each other. Now, for the one that's deflected at an angle greater than 90 degrees, the question used to have about one and this A and C. A and C. The one get reflected at an angle greater than 90 degrees. Why? What do you have? What do we need there? It can be deduced that the nucleus is massive, or another is having charge, is charged. In another way of putting it this way, another way of putting it to two now. That is, most of the mass of the nucleus is, okay, let me write it down. This is another way of putting it. Most of the mass of the, so you can write this one down, is at the center. Two, that's the way of putting down the nucleus is charged. Sorry, nucleus. Sorry. Okay, let me. Is charged. It's a two-mark question. So what can it be that is from most of the other particles that are degraded at an angle greater than 90 degrees? That's two mass question. So put it this way. So split it this way. So write it down this way. So most of the mass is what? At the center, and the nucleus is charged.
Yes.
Can we proceed?
Yes, sir.
Okay, fine. That's good. It's very interesting. Now, another one on that note. I will say you don't know. So when you see something like put note under my note, make sure you study those things. They are very, very important. That's why I used to put the important points in that way. One of the Why do we choose gold? Gold was chosen. Why? One of the reasons choosing gold was that it can be made into anything substitute. Another thing, now there's an apparatus where the experiment is being carried out. So the air inside the apparatus must be pop out. Why? Because little centimeter of air can actually stop the alpha particles. So that is why. So little centimeter of air can do what? Can stop alpha particle from passing through. So if air can, do you know the meaning of that? Let me comment. Now let's say, so the implication of this is this. Let me put it this way. Let me just quickly put it this. Now, here now this is an experiment. Then they carry on in an apparatus, and you have the whole this place. Let's say yes, yeah, it's full of air. Now you pass alpha particle. Now alpha particle can never get to the nucleus. Why? Because it will have been absorbed by the air. So that means the experiment is not going to work. You can't even detect whether some will pass through, whether some will be deflected, or some deflected back at an angle greater than 90 degrees. So you should know that. I think you should understand now why the air has to be pumped out so that it will not absorb what you want to use to carry out the experiment. Now, another thing, when you have, if a thick foil is used, more of our particles will be deflected to backward. Yeah, it will be deflected backwards. It will be deflected backward. If you also use, what do you mean by a thick foil? So this is what I mean. Come and see. If this one is heavier, far heavier than this, that means this one cannot even pass through at all. Almost everything will be reflected back. So that's what that statement is saying. Now, if you also use if you use a tin foil here, that means almost everything will pass through, because this one is less than this in terms of mass. So in terms of speed as well. So that means this one will have higher speed and also heavier. That means it can collide with this and bubble it out. So almost everything will pass through. If everything passes through, it has violated the rule that says, number one, nothing will be deflected back. Nothing will pass through deflected small at a small angle. So you only have only one passes through, which does not actually miss it. That's what even J.J. Thompson is saying. So are we together?
Yes, sir.
Okay. So that's point there. Now another point you have there. Now, okay. Most of our possible pass through a small angle can be deduced by nucleus is that's another one, small angle, yeah. Nucleus is small compared to the mass of the atom. So what are the results? The question says, what's the result of alpha particle scattering? So they are looking for these two. So this is number one and two. These are the major results of the alpha particles. So that's that. So let me move on to the next one before I look at it. Now I want to be picking this one after the other. Okay, no, still continue. So why don't we use alpha particle? We don't use beta. Why? Beta have range of energies. Beta they are deviated by electron. So what I mean of that? You have this is a nucleus here, solid nucleus here, and you have beta particle. So this is beta, either beta plus or beta minus, beta particle straight. Now, when you have this beta particle here, you pass incident this, so that means deviated. That means it will deflected by our electron. It will deflect like this. It will bend like this. So what happens to the one that passes through? Nothing. What happens to the one reflected by nothing? So that's why we don't use upper particle. Because upper particle will deviate what? Electron. So that's all. Upper particle have very small mass. So those are the reason we don't use that. Now, all this I won't waste more time on this because do you also take chemistry?
Yes, sir.
Do you do chemistry?
Yes, sir.
Okay, so that's I don't want to wait. You understand all these points in chemistry language,
Yes, sir.
so that I'm not waste our time. That's why you understand all this proton, neutron. No, let me waste. Same thing here. Let me just go. We don't need those ones. So isotope as well. So isotopes are nuclear of the same what element with different. This is the way we want it to define in physics. This is the way we want it. Okay. So different number of neutrons, but same number of protons. So that's the definition of it, the way we want it. Now, isotope continues. I don't need to go to waste more time on this. To go through, you
Yes.
understand this. And these are also basic string chemistry. Like the same thing. I'm just trying to explain better. So it's still the same thing in the notes. So okay. Now, we have example one here. If the guideline says describe in details a Uranus war two atom of this or 235, it's a 4 mark question. This particular question I say 4 marks question. So meaning that you have to talk in terms of proton, you talk in terms of neutron, you talk in terms of what? The electron and charge. Each one is 1 mark as you see here. It's a 4 mark question. So you have to describe this. So for you to know the number of protons it has 92. To get the number of neutrons, you subtract it from here to get neutron. The same thing, number of neutrons is the same thing as electron, provided it's a neutron. Yeah, it's not charged. It's not something like maybe A3 plus. This one is different. Now, with reference to two forms of this, explain in terms of isotope.
Say,
This fellow did not ask
what,
to define isotope. Yeah?
why is the charge zero?
It doesn't have a charge. It's a neutral something. When you have, for instance, in your chemistry, when you have A, let's say you have A3C, let's say, for instance, so you have H2SO4. As long as you don't put something here, this charge is zero. Doesn't have any charge. The way it is zero. But if you have something like this now, it's having a charge. This one is having charge now. It's having charge. The charge is plus 3. But when it does not have any power like this, it's zero. So it's a zero. This one is a neutral atom. It's a zero. Is that okay? So it does not have a
Okay.
charge. So that's so you have to define the question does not ask us to define isotope here. It just a reference to this explain. So what can you say? Nuclear same 90. They have to, yeah, both of them have the same 92 and they have different what neutrons. So that's what we're saying. It's not say define. So you should know what the question asking to do or what we have to say. So reduction to let me see whether I was okay. I think I need to spend yeah, we need to continue from here later. Went fine. That's why I'm going to family of we are going to this thing now. We have one the nucleus of the nucleus of stable decay, they emit alpha, beta, radiation, and other things like that. So let me pick it from it. There are two types of beta what radiation. We have beta plus and beta minus. Beta minus is an electron. Beta minus, beta plus is a positron, positive charge. So beta minus is an electron. So this is a positron, this is electron. So when the two of them combine together, they will annihilate each other to form two gamma radius. If you have this equation like this, you have beta plus beta. You can also use E, beta minus. They form together is going to give you one gamma plus another gamma. So what happens? The two of them, the language is annihilate. So annihilation has occurred. The two of them annihilate each other to produce two gamma radiation. So when you have
Yes, sir.
when you have a beta and what, so take note of this. Take note of this. Now, as a way of the achieving the greatest ability, okay, that's not even. There are two types of this. Okay, fine. Beta minus is called electron. Okay, it's also called positive. I think it's here. Oh, this is even the place. Okay. When a positive collide with an electron, they annihilate each other. Their mass is converted into what? Electromagnetic radiation in the form of gamma. So it forms two gamma photon, two gamma rays. So that's the discovery of neutrinos. So I'm moving to the family of this thing now. This discovery of neutrino. When the are formed by a decay of beta or a beta particles. Beta particles are emitted by the range of space, some of these gamma. Now, when some of the energy and momentum released were carried away by another particle. So what's the name of the particle? We have something called antineutrino or electron neutrino. I think the symbol, something like V, put a bar on it. So this antineutrino, or we call it electron antineutrino. So that means decay of beta minus. This decay of beta minus. Now, for decay of beta plus, it's going to be neutrino or electron neutrino. It doesn't have any bar. That's different between anti. That's different between this and that. Now, this now you must be able to write the equation of ant. This particular equation of ant. Take note, please. You must write it of ants. You must be able to write it like this of ants. So this one proton and neutron proton. So neutron decays to form a proton together with what an electron alpha part. This is what beta minus. Okay, I can write in this way. That is one neutrino. Neutron decay to form proton. So this is a beta. This is a beta minus. So this is a beta minus. You have here. That's minus one charge here. Then plus electron neutrino. So that's all the same electron neutrino. Can use the beta minus. The same thing when you want to form, you want to produce a proton. So your proton start from positive. If you are to produce from yes a neutrino, this neutrino, so you should be able to know the equation of and also be written in another form. What is another form? I will let you know later because this proton is called UDT proton. That's what is called. I forgot the term now. Quark quark composition of a proton, UDD. So for the neutrino, for the neutron is UU. Okay, sorry, UUD is the proton, UUD is a neutron. So this one is neutron, this one a proton. This is called quark composition. Now I will be able to write in form of, okay, maybe I will see later. I want to write this in type of this. You're able to write this like this. Two of them have to match them together. So now, in case of this, take note of this particular when you note it, therefore the number of the one that are conserved. The mass is not conserved, but there's something called mass energy is an entity. It's a single word, mass and energy. That's got from Einstein. So mass energy is conserved. This is conserved. Energy is conserved. Proton number. So you can see now, proton number is equal this know the relation between energy and this. So this is the mass, the speed of light, which is 3 exponential 8. So this is the mass. This mass is called mass defect. So, but we don't really need it much here until in A2, we are going to look for change in mass of the product and the reactor. Okay. Now, what's our particle? I corrected this there. Another particle is what? If I have to define our particle, the reason is what? As contains what? Two protons and two neutrons. That's all. What are the properties? So property, I think you can go through all this property to just memorize one or two things here, and should be based on what you also know before property. But this is the definition of a particle. It has contains two protons and two neutrons. The same thing, beta particle is an electron. This is the definition. So what are the properties? These are properties. The property of a beta particle is in between alpha and the gamma. So they are in between. They have just something like called semiconductor between uh, conductor and insulator in between. Now, this all the gamma definition is what is what electromagnetic radiation. That's the definition of all this. Difference between alpha and particle. You can use definition to define to differentiate. You can also use their property to differentiate, pick any property to differentiate those. Now, family of fundamental particles. This is one major aspect of this. Fundamental particles they are grouped into two. They are called hadrons and leptons. Fundamental particles grouped into two. Hadrons and leptons. Now, okay, 3, 4, 6. Okay, I'll put it. Now, hadrons are what? There are particles that are what? Affected by strong nuclear force. First of all, no Guerra, take note of this. Affected by strong nuclear force. So it means they are not affected by weak nuclear force. That's another way. Take note. They are affected by strong nuclear force. So they are bands of quarks. There are 6 levels of quarks. Initially, there are 6. Now we also consider the whole 6 here. You must know what each one, the symbol, the charge. You don't really need this strange. You don't need this one. But major thing is this symbol and the charge. Flavor of quarks. Of
So,
quarks.
so I
Yeah.
have to know all those charges and the flavors.
You say what?
I'm saying I have to memorize that whole table.
Yes, yeah. You have to memorize this one. You have to memorize it. You have to. I will show you like not just like I send you some questions. Not each topic I have compiled question called topical question. I've done it myself. That's why I thought I also send you to under waves, the question under waves that I sent. So by the time you see question now, you will see. You must memorize this. Up quark. If you discover up quark, this is very easy for you to know. You can use this one. Let's say 1, 2,
Sure.
and 3. Yeah, you know it together. Why? Because they have the same charge. You also know this and which one, this and this together. So that's all. It's a simple way of just to memorize it. Simple way. So you have to know the charge. Each of them, the up quark, the down quark, the straight quark, charm, bottom, and the top quark. Now we have here we have hadron composed of baryons. And there's something called baryons and mesons. Baryon has 3 particles, 3 quarks. 3 quarks have no. It can be U, D, D. This is called baryons. This is what 2, maybe U, D. This is called 2 meson. So baryon consists of 3 quarks. Okay, so I have meson consists of quark, which are one. For these mesons now, one must be a quark, one must be anti-quark. For instance, if a quark like pi now, a pi meson means 2, but one must be anti. If this one is a quark, let's say a quark is this. Anti-quark is going to give you D by D. That is negative. That's not anti-D. Anti. Let's say up for up quark now is U. Let's up quark is U. Now anti up quark, that will be what? By U. Do you get the logic?
Yes, sir.
Okay, that's not anti. So it makes us have to consider one must be a quark, one must be anti-quark. So this is a 5 meson. So you, for instance, a proton. This is a proton. Proton belongs to baryon. Why? Because it consists of what? 3 quarks. And they are what? Hadrons. So you have to understand a sample, just like let me put a sample of this now. A sample of these hadrons now are So let me write here. So example of these andros are example 2, we call the proton. Okay, is everyone okay? They are here. Protons are what? Neutron. They are example. Case of paper one, you see all this in paper one. So these are example of this, both of them. Now the three of them, these two, they belong to something called a barrier. Why do I mean it? Because they are three quarks. You can see now three quarks. This one is UUD. UUD. So that's three quarks. UUD. While this one is UDT. So three, 1, 2, 3. So they are example of they are hadrons, and also they belong to the class of cobarium. Why? Because they compose of three quarks. Three quarks. Now, you know what's the charge of a proton? That's plus E. So how do we prove it here? So that's why we prove it out here. So you can see now you have UUT. So that will give me 2/3 E. You know, an up quark. If you go and remember, if you go and check the chart, it's 2/3 E up quark.
Yes.
So if the same thing. A down quark is minus 1/3. So add up, we are going to get it. So that actually consolidates or proves that the charge of a proton is positive. A neutron, does it have a charge? No, it does not have a charge. How do we prove it here? It's under this topic, we prove it. It's what? UDD, which is equal to what? Up quark 2/3, a down quark minus, a down quark minus. Add up, you are going to get 0. That actually shows that what? It does not have what? A charge. Are we together?
Yes, sir.
So that shows we don't have a charge. Cool. Where am I? Okay, where are we? No, that okay. Okay. If a quark is this, the charge of an anti-quark is this. So and this will be the anti-quark. Is minus. Now, leptons affected by what? Weak nuclear force. They are affected by weak nuclear force. So that's even the way to put them. What are leptons? They have particles affected by weak nuclear force. We have example. Example are called electron, neutrino, and all this is okay. This is example neutrino, beta plus, beta minus. Sorry, note it down. They are example of electrons. They are example of electrons. So they are not affected by what? And they are not bonds of quarks. They are not. So they decay to become up quarks. They are not bonds of quark. Now, this is what we have the other time. When we want to form electron. Let me bring to you. This one is the same thing as the other one. We must know it. Let me bring this. Now, I have a neutron composed of these to form a proton, then beta minus 1, 0 plus this electron to neutrino. So how does it give this? It's equivalent to this. How? So how do we get that? We get that in this way. Remember, we said this was a neutron. UDT. What was this one? UUT. I don't need to write, but let me just first of all write it out. Yeah, minus 1, 0, the electrons in. So if I look at it this way, you will strike out a D, you cancel a D. A U, you cancel a U. What are you left with? You are left with what? D here. Changes to, what do you have? U. You are left with a U, an up quark, then plus a beta minus, then plus electron at the neutrino. That's what we have here. So meaning that during decay of beta, so I want to write something. So during decay of beta minus. Now,
So why did
uh,
you say you are left with the U this side? Didn't you say that U cancels out the other one?
is that
Didn't you
what?
say that U cancels out the other one?
And yes, yeah, it counts. Yes, now you can see a U here. U takes away U. U takes of this. But you want to put it when you say during the alpha, when you were beta minus decay. This way to not to cancel. This way to put it. The question is going to be in this form. Number one, a particle is formed called electron and neutrino. Two, a down quark, the a quark changes. Because the question I ask you, write a change in quark or quark changes that takes place when an beta minus is produced. That means a down quark changes to an up quark.
Upcon.
So yeah. So write it. So during the decay of beta minus, so write it down. During the decay of beta minus, so a down quark changes to an up quark. So that's so write it down at your end. So during the decay of beta minus, a down quark changes to an up quark.
Yes, sir.
Okay, that's it. So you must know these two equations together because you might need like this and also like this. You must know these two together offhand. You must be able to write offhand these two, this one, and also this one. So it can be this. At times you might need like this or like this. It depends on what you want to do in the question. Is that taking?
Yes, sir.
Now for the second one, if you also do the same thing, you describe the same thing. So look at if I so okay, let's just do this one. For this one that say so this one mean up quark changes to what? A down quark.
Down clock.
Okay, yeah, plus one. So this that's electron neutrino, not anti. Where is it coming from? You can see this one up quark is from where? From proton to then you have beta plus, you have plus one and zero, and you have this. So if you do it now, if you do this, what are you going to get? You are going to have this a proton with U T, so plus U D T. So that will be, oh, sorry, that should be this to this. Sorry, decay to this. So that will be plus one, zero. So that's all. So that's what you have there. So if you do that again, you discover that you can see a U will take off a U. One D will take off one U. You are going to have what? What are you going to have here now? U,
An up clock
yeah,
is opposed to a down clock.
thank you. So now plan changes to what? A down quark. That's all. So during beta plus or positive. So an up quark changes to a down quark. So that's all. Now, behavior of this, that's the major thing. The behavior of electromagnetic, when you have the one more the most deflected one is going to be beta particle. So beta particle get deflected towards the beta is a negative towards the positive, then alpha particle, this one passes through undeviated. The same thing under electromagnetic field. This also passes through the same thing here. So this one deflected one. So you have this one means electric field is into why is he deflected? You understand when you get to it to under electromagnetic we're going to Fleming's left hand rule to determine this. No. So that's the summary on this. But let me show you how the question used to be here before we move on to. So I have questions I've compiled here. I think I even done something on this. So let's quickly look at those things before we move on to this. I think I have paper one of it, I have paper two of it. But let me go and find it out. Tonight I have it somewhere. The activity we did. Okay. Okay. Can you see my screen?
Yes, sir.
Okay. These are compiled questions on that. Have them here on this. Solve them already. Now, we see what I'm saying here now. Let's see what say the name of the world where they belong. You can see now electron. It's an example of what electron. You can see neutron, hadron. You can see neutrino. You can see this. You can see what I'm saying. That's why the question used to be. Now, for this particular one now, the question says you have to complete this. So this is not there. They just write P and N. You can see my pen was when we wrote this. So how do we, when I see proton, I know that I'm going to form electron neutrino. So I know what to for. And that's why I say you should know the question of hand. By the time you know those things, you should know what to. So if I have this now, I know normally if I'm to have one P this, definitely it's going to give me better. That'll be it's going to give me better plus. That'll be better plus. That'll be zero. So that'll be what this. So this one does not have a charge, it does not have mass, it doesn't have neutron of this. So that's all. Once you know it of hand, it doesn't give you any. Okay, I've omitted something here. 1 0 on this. Okay, that's all. So look at this one too. Still, what is the force responsible for decay of what? Of the decay. Hmm. The decay is what? As long as you are forming, as long as you are producing either this or this or this or this. Any one of this. Any reaction that gives you this, you should know that it is from leptons. And leptons are what? Affected by what? Weak nuclear force. So what was the force responsible for the, can you see now? Weak
Yes,
nuclear
sir.
force. Yeah, okay. So that's all. So as long you are having any of these, you should know it's going to be weak nuclear force. So you can also have so difference between particle and this. This one is different. This one is actually they didn't say one I have my note difference between alpha particle and beta particle. But this one is this specific difference between disagree between alpha particle and beta plus. Beta plus, not ordinary beta particle. Because beta particle consists of beta plus and beta minus. Alpha particle have two protons, define them. So what was the beta plus? It's a positron. Another point, a charge. What was the charge of this one? Beta. It's a beta is a what? It's a, this one is plus one. Beta minus minus E. Beta plus plus E. So this one is a what? Another one. Why this one is a what? Alpha particle. Yes, alpha particle. What's alpha particle? Alpha particle is having four. In fact, we are going four. Am I right? That
Yes,
four
sir.
what? Four neutron. No, these two what?
All nucleons.
Is going to have two neutron and what? Two proton. Am I right?
Yes.
Okay. So what's the quark composition of this one? It's even good. What will be quark? Remember, that will be D. A neutron is what? U, D,
E.
D. Thus, the proton is what? U, U, D. Yeah, do it. Open the bracket. So that means it's going to have 6U and 6D. This is a quark composition of alpha particle. Take note. How you say 6U, U, T. Anyone. Yeah. So if you open the bracket, because you are going to have this, you are multiplied by that will be 2U, 2D, that will be 4D now, 4D plus another 2D, that will be 6. 2U, that will be 4U. That's it. This is a quark composition of alpha particle. It's having two proton and uh, two up quark, 6 up quark and 6 down quark. And one thing that contains of proton and neutron is their hadrons. They are not leptons. So that you can see the difference now. So take note of this, write this thing. So take note of this.
Yes, sir.
Okay. Now this I will just go to 1 or 2 here. So I will give you this. You will go through it at your hand there. So I've
Yes.
done all this. Okay, give you this. Let me just see one or two things more. See, you have the same thing. So write all this. Be able to write the equation. What was the proton this use and this? How do you prove that it's having plus charge? That will put in the formula. Let me just see where I need to talk. Take note of what I put here. This when you see the nerve. So because neutral and proton are example of hadrons. Hadrons are bands of quarks. They are bands of quarks. Label the look at this type 2. I compare this to this. So this is what we are given. So I have to write my own somewhere here so that we know what X represent, what Y represent. So what the name of this symbol, electron, neutrino. So what kind of this form? Okay, I don't think I put this thing there. Say the form of energy, called the kinetic energy of the product, or of the inside of, you can say, of the fragment or product. And also another point, there's another one, gamma ray photon energy. Gamma, there are two. In case there's two marks, state the two. So gamma photon. Yeah. So it's either this or this. So that's form of energy. Let me just no. I'm looking for this type of question. You should able to. So the question is saying when it form nuclear. So we are moving from where to where. I think in the case. Like just subtract, you see what the new one is going to give me. The new one is going to give me this, and this. I think that is just something you just. I'm very sure. I'm looking for. They are the same thing. Same thing. If I say, okay, you. Okay, that's what where I started from. So I just want to show you question on it. So that's where how the question used to come. So one of the results of our particle is what the majority of these were are scattered through angle greater than 190 degrees. States what may be inferred. What does that one mean? Majority of the mass is at the center, and also what the nucleus is charged. So that's all. As I said earlier in the notes. So that's how you will see the question will be asking you. So it is not a fundamental particle. Why? Because it is made of quark. So why I see alpha particle here, alpha particle there, they are not fundamental particles. Why? Because they have neutron and proton, and they are example of what is called hadrons. Hadrons are not fundamental particles. No, only leptons are fundamental particles. Only leptons are fundamental. So that's all. So let me just say, so you go through this, you go by the time you go through this, you see, yeah, later goes of visiting. When you read through this, you get the understanding better. So that's all of that. Um, you you made mention of which other topic you made mention first. You say apart from this topic, which other topic you say is challenging as regards to your exam, your test, exam tomorrow? Which other topic you do say?
This is again.
Okay, this other that's electricity. This
Yes.
electricity. This I don't even have it separated, but I don't have electricity. So let me go and find the node under electricity and electricity. this is so okay. I will just okay. That one, I think it start from the all this internal resistance, electromotive force, and the terminal PD. That's where the DC this thing start from. Because I don't have it separate. I used to have a whole complete. So in that case, but I know it's separated in the syllabus. For me, the fact that electricity is straightforward. So let me see. So let me pick it up from here, and that's where this is something we have to start from here. This is like so to be from here. Let me pick it down from here. Yeah, spread all this formula. Let's check if it is okay. Not all this point. Okay, fine. Let me just quickly go to it from here. Yeah, to begin from here. No, not all this. Internal resistance. Yeah. So internal resistance, what do we do? How do we define internal resistance? Resistance of a cell that's actually causing the loss of what? Energy loss in the cell. So
Yes.
it's caused its energy of the cell. Now, uh, let's say you have, for instance, let me just bring this explanation here. I don't be useful. You have a DC battery, car battery. It's 12 volts. That's 12 volt. That car battery, your daddy's car or your own car battery, 12-volt battery. If you also have another Tiger, that small Tiger battery, each one is 1.5 volts. Each one 1.5 volts. If I have 8 of it, 8 multiplied by 1.5 volts, it will give me 12 volts. If you gather 8 of 1.5 volts together, 12 volts, it can never start a battery, a car. But if you have ordinary that big battery of 12 volts, both of them they are the same 12 volts. This one will start, but this one will not start a car. Why? Because the smaller the cell, the higher the internal resistance. First of all, take note of that. So if you have a bigger, the internal resistance depends on the size of a cell, of a battery. If you have a bigger battery, then the internal resistance is very small. Am I communicating?
Yes.
If you have a small battery, you have higher internal resistance. So this one is having higher one. By the time all the internal resistance combined together, that means a lot of energy will be lost in the cell. So you have only small one that can power the car. So that's why it's not enough to power because of the greater the size, the smaller the size of the cell, then the higher the internal resistance, and the more the energy lost. So that's what you need here. This is what you need here. The definition of this so now EMF, terminal PD, you must be able to define the two. What is EMF, what is terminal PD? For instance, you have a battery. Let's say you bought it new, it's 1.5 volts. Then you connect it to a voltmeter, a voltmeter source, and fine. So a voltmeter, you connect this battery to voltmeter, and it gives you 1.5 volts when you read it. So that 1.5 volt is called EMF. If it's 1.5 volt. Let me explain it better here. You have a circuit. Fine. A circuit is here. A battery is collected in this one. And that means the key here. Then you have a voltmeter. Fine. In this particular circuit now, the voltmeter here, let's say you have this battery is 1.5. The voltmeter will read 1.5 here. That is called EMF in an open circuit. But immediately you close this key, let's say you close this key like this, bam, it will be less than 1.5. The value that you are going to get, which is less than 1.5, is called terminal PD. It is called terminal PD. So meaning that terminal PD is always less than 1.5. Terminal PD is the voltage that is obtained in the closed circuit after EMF has lost certain amount of value. So that's called terminal PD. But that's not the definition I'm just using to explain now. So is the EMF obtained after a cell has lost certain amount of voltage. So the remaining voltage is called terminal PD. How do we define it? Is the energy, it's a two-mass question. Two-mass energy transform from other form to electrical. This is one mark. In fact, energy, this energy transform, this one, from other form to electrical is one mark. Now, per unit charge here is another one mark. That's the keyword. That's what we want to see. That's what we want to see. So energy transform from other forms of energy to electrical. That is called EMF. Now, it's the opposite now that we have this. This same thing. Energy transform from electrical to other form. Energy transform electrical to other form, to others. So to other form, that's one mark. Per unit charge is one mark. You can put it this way. You can say energy transfer per unit charge from others to electrical. That's EMF. You can say energy transform per unit charge to the unit charge from electrical to other. That is terminal PD. Any question?
No, sir.
Okay, so that's terminal PD. So we now have terminal PD is less than what? EMF because of different gives lost fold. There's something called a lost fold. And that happened because there's something called internal resistance. Internal resistance of a cell transformed to internal resistance. So we have this particular circuit. So this is the formula that contains the two of them. You have V can also be small v here. This one is called EMF. This one is terminal PD here. Terminal PD here. This is IR. This one is lost fold, smaller PD, smaller V, I, small r, internal resistance. So it can be written like this. So that's all EMF. Now, when we have this, I remember something. I escaped my mind. I want to say something. Something came to my mind. I don't know why it escaped my mind. Okay. Okay, if I remember along the way, I remember right now, I don't know. It escaped my mind. I remember something I want to say. Something just dropped in my mind to say it, and which is very good. Well, let me think about it. I remember later. Now, you having this equation. Okay, I've gotten what I wanted to say. For instance, you have let me have a circuit in this form. You have a circuit in this way. And you have internal resistance like this. You now have you can have as many for instance you have this connected this way, let me have a load a comma and you have this. In the question, that's how the Cambridge used to do their home. They have to put some, if it's having internal resistance, they have to put dots like this. So that means there's internal, this one means there's internal resistance in the cell. Now, this one means there's internal resistance R here. Here is the EMF here. And you can have your R1, bigger one, R2, the R3. All this, anything, any resistance that is outside this closed dot broken line, we call them terminal PD. Anyone that is outside this, we call the terminal PD. We call the terminal PD. So these are called terminal PD. For instance, all this, anything that is outside here, from here, down here, we call the what? The PD across is called terminal PD. That's all of them are called terminal PD. So you have to combine them together. As long as it's outside the broken line, it is referred to as what? The PD is called terminal PD. So if you have to define, let me move you this now. I don't know. This is just coming to my brain. You know what I like doing? This is what I like doing. I like this kind of, they're just teaching. I like it so much. Especially when it comes to my subject, forget about this A-level stuff. I like it. That's how you see. Now, let me disable this. See this. Another one. So that's how to distribute EMF. Okay, it's okay. This EMF will be distributed into two. This EMF you see here must be able to now to distribute EMF. In fact, that's what even make your work. That's what even make it easier for you to tackle. This EMF now. EMF, yeah. So how do I distribute EMF? So let me distribute EMF. One comes here to internal resistance. Another one comes to these, all of this, because they are outside. Can you hear me?
Yes, sir.
Okay. Now, if you have to now write a formula for this, that means EMF is equal to P across V across R, which is small letter V here, plus V across all these three R. That's all. So that was going to be V across this R. So must be able to distribute EMF like this for you to know how to do it, how to work. Okay. So here now, this is potential divider. A potential divider, okay, I have to connect it to thermistor and a light dependent resistor. LDR. So we have a potential divider. What was the name for potential divider? Now you have a voltage. That is what you needed is actually more than what is available. And you don't know what to do about it. For instance, you have the input voltage is 9 volts. You just need about 5 volts across a particular section. That's what you need. So in that case, a potential divider is applicable. Potential divider is to divide the voltage, the PD. How does it work? So this, I just have a single one. Let me try to draw another one here. Now, you have, let me try to say I have it here. Let me try to draw another separate. Okay, you can give me R1, R2. So the same thing like this. Now, V out, it can be anyone. If I like, I can place my V out here. I call it my V out. If I like, also I call this one V out. Anyone, V across this V out, V2. So if I have a V here, that's the same thing like this. So if I want to calculate V across 2, which is V out, or let me even say V2 self. Let's say this is V2. If I want to calculate V across 2, the rule says I'm going to say V across 2. That will give me resistance of that 2 over, you add it together. Then multiply by total voltage, V in here. If I want to calculate resistance across, let's say I also have V1 here. If I want to calculate across 1, I am going to make use of, I'm going to use across 1. That means I'm going to use V across 1 is nothing but resistor of 1 over resistor of 2 plus resistor of 1 or 1 first, anyone, 2, multiplied by voltage. That's how it works. Now, what was the we need to spend a little, I have to explain it better. What was the implication of this V out? What was the implication of this V out here? Can you hear me?
Yes, sir.
How does it work? Because we have to connect it to what is called thermistor. What's the thermistor? Thermistor is affected by temperature, depends on temperature. It's a,
Yes, sir.
it's a something that actually senses the voltage. That's temperature. There's something also called temperature radar. So that was the same. It measures temperature. So there's another called light dependent resistor. We need to connect it to a potential divider. We need to connect it to a potential divider. How do they work? Now, a thermistor is that when you have a thermistor, as temperature increases, the resistance will decrease. That's a thermistor. That is, resistance increases as temperature decreases. So, relation between resistance and thermistor, the temperature, they are what? They are inverse for thermistor. thermistor works with that's a temperature, depends on temperature. So the resistance of thermistor is inversely proportional to the temperature. So note it down.
Yeah.
The resistance, okay, of a thermistor is inversely proportional to the temperature. That's that. The same thing with light dependent LDR. LDR depends on intensity. Light dependent resistor is affected by intensity. Light dependent resistor is affected by intensity. Now, the resistance of the light dependent resistor is inversely proportional to intensity. Am I making sense? Is it getting clearer?
Yes, sir.
Okay. So the resistor, they are both of them are inverse. Now, what you need to know now is that okay, let me get a blank page. I need to write somewhere. Yeah, let me write so that you need to get this because these are the major aspects you need on the electricity. These are the things that you need on the electricity for you to excel well on the electricity. Electricity and waves are the major topic. In paper one self, the question start from number 20, number 21 to 37. Waves and electricity. 30, other 30 or 30 is 39, 40, particle physics. But the remaining topics are from number 1 to 20. That's how it used to be. So the two topics carry a lot of weight. Okay. Okay. Can you see? Wait, is it hearing? Am I hearing?
Yes, sir.
Okay. So that can we can move from one point to another. Now, quickly, for thermistor, the temperature, and the light dependent resistor, you need to know some things. I need to ask you question, but you are the one to answer the question from here. But let's explain it now. Then you understand how it works. What you need here. These are the things you need to do. Okay, let me come again. Let me just use only one here. Like, let me draw it again. We need to do some calculations now. I want you to understand because that's how you're going to be in the theory. You need to, for instance, let's say you have 9 volts here. Here is 3 ohms, and here I have my 8 ohms. What happens? I want to look for voltage here, V here. Let's say V across 8. I want to look for it. So let's calculate it. Then we'll change it again. Then from there, we're able to conclude what happens. So for instance, I'm looking for V8. So that will give me 8 based on the formula 8 plus 3 multiplied by 9. I do have a calculator. Let me see. Yeah, quickly. What's it going to give? That's 8 over 11 times 9. What's it going to give?
So it's going to be 6.5, 0.54, 0.55,
Okay,
0.55.
6.55. Okay,
Yes, sir.
6.55 volts. Now, if I want to calculate across three now, you don't need to calculate, just subtract it from 9 because total is this 42. So if I want to calculate V across three now, let's say V. So in this case, I have V across 8 as 6.55. So V across three now. Yeah, calculate it. Just subtract it from 9. Or if you follow the method, 3 over 3 plus 8 times this, same thing. Or subtract it from 9.
2.45.
2.45.
Yes.
2.45. Fine. Fourth. Okay. This is where I'm going now. Let's now say we change the resistance. Let's say we decrease the resistance of this one. So what happens? I have 8 now. I want to decrease or I want to increase. Anyone, I can decrease, I can increase. Okay, let me work on increasing. Let me say I want to increase. So I increase it to 20. So what's the effect of increasing to 20? Yeah, let me increase to 20. What's the effect? Because this that you have to know this in the theory part. So increase the resistance of this one. So what will be the new V8 now? V across 20 now. I've increased this one. What are you going to give me? So that will give me, if you increase this one, so that will give me what? 20 over 20 plus 3. Yeah, calculator. Now, what will you give? The new one now, new voltage. So if I increase this, what happens?
I think it will decrease.
If you
7.82.
increase, no, no. What is
Say
it?
7.82. It
7 point what?
increased.
Uh-huh.
0.83. Increased.
Okay, it increased 7.83. I know 7.83. So if you also, what happened to this one? If you look for the, that's the one with decreased. So you can see where I'm going now.
Yes, sir.
Where I'm going is this now. So whatever happens to resistance happens to voltage. Note it down. What am I saying? That is, if resistance increases, just know that the voltage across that resistor also will increase. You know, when we
Yes.
have eight,
V equals to
when we
IR.
have eight, thank you. When we have eight, we have 6 point something. If you increase to 20, what happens? This also increases. So take
Yes.
that's all you need to know now. Now you can see now. So whatever happens to resistance happens to voltage. Now coming to thermistor. Let's now say for on thermistor, you have the temperature is 30 degrees C, 30 degrees C, and uh, the resistance. Okay, let's say okay, yeah, of course thermistor. Thermistor did the symbol like this. This is the symbol for thermistor, something like this. No, you don't even need this one. You don't need this one. Something like that. That's thermistor. Now we have temperature, 30 degrees. Now let's say you increase this temperature to 70 degrees C. What happens to the resistance of the thermistor? Then what happens to voltage of the thermistor? Later you get the logic because these are the way they ask you to ask questions. Let me come again. Temperature of the thermistor is 30
Resistance
degrees
will
C.
increase.
We now increase the temperature to 70. Temperature increasing. What happens to the resistance of the thermistor?
It will decrease.
Thank you. What happens to the voltage of the thermistor? Across the thermistor?
It will increase.
Come again. We started here. And I said, whatever happens to voltage happens to resistance. So if resistance increases, voltage increases. If resistance decreases, voltage decreases. So get it right. Now, if you now increase temperature of the thermistor, the resistance of the thermistor will decrease. Yes or no?
Yes.
So what happens to the voltage of the thermistor?
It will also decrease.
It will decrease. That's it now. So that's going to happen. So this is what's going to happen in the theory question. Yes. When you say state and effect, because I just tell you this and this, now say the resistance is double or the temperature is double. State and effect. States and explain the effect on the thermistor, on the voltage of the thermistor. That's how the question used to be. So you should know that if the temperature decreases, resistance will increase, voltage will increase. So take notes, just write it down in your language now. So if temperature decreases, resistance increases, voltage increases. Also,
Yes.
if the temperature increases, resistance decreases, voltage decreases. So take note, write it down. Does it make sense?
Yes, sir.
Okay. So that's how it works. So the same thing for light dependent resistor. The same thing. Instead of this one, if I say intensity, if intensity was 30 before, you now increase it to 70, same thing. Because if intensity increases, resistance will decrease. Then PD also will decrease. So take note. So whatever happens to, if you have a resistance constant, voltage also will constant. If you have resistance to decrease, voltage also will decrease. If you have resistance to increase, voltage also will increase. So take note of that. Now, moving on to a potentiometer. So a potentiometer is the one that we used to compare the EMFs. We used to compare EMF. Because we used to compare EMF, you look at it here. So potential consists of a piece of resistance of one meter comparing potentials. For instance, EMF. Say if I have a measure resistance, how does it work? the uh, the PD increases with length. So take note of that. So the higher the length, the higher the PD. In fact, this is
Yes.
even correct. Uh-huh. Is it, why am I saying is correct? Why am I saying it's correct? It will go back to this
Because
particular formula under resistivity. Uh-huh.
not lens.
Very last one, L. Am I right? This one very
Yes.
last one over
A.
A overhead. Say, thank you. So the higher the length, the higher the resistance. Don't forget, I also say resistance and voltage are like this. So take note. So this is how
Yes.
it works. So the higher the length, the higher the voltage, the higher the resistance. So throughout the whole length here. So when you have length here, length is 0, no PD. So as you move down like this, length increases. PD
Crazy.
also increases. Thank you,
Yes.
increases. So I like that. So I like their hair. That's kind of what I like. Thank you. Now, so this, the PD of this, if I have to calculate unknown, okay, this one is unknown now. For potentiometer, you must know one PD. You have to know distances, you know one EMF. Then you are looking for the unknown, one you don't know, one that you don't know. For instance, so you compare with the distance, increase with distance. So this one is correspond to this X here. Is correspond to the distance A this. This or this, the EMF here, E naught is also correspond to distance everything AB. AB. So how do we generate the formula? This is what I did there. It's a very simple thing. So when I have V very large what as L, so meaning that my V1 over L1 is equal to V2 over L2. Now, if I go back to them, if I pick this one as my V1, E as my V1, that means my L1 is AB, the total length. This is for this. This one is for this one, total length. So if I pick this as my V1, total length is AB. So I am going to have it like E naught over distance AB is equal to, if I pick that EX as V2, the distance will give me EX correspond to the distance from A to Y. So that will give me AY. So that will give me AY. So if I'm looking for ES now, so that's why I have the formula. ES is going to give me what? E naught times AY over B. So that's why I have the formula here. So that's how it works. Just know this.
May
So
you
that's
please
okay.
explain that again? May you
Is
please
that
explain that again?
okay? Okay.
Yes.
And let me explain again. Okay, fine. If you let me explain here. If I have this is this. Okay. This is the length. So this is the length. This is the length. I can call the length AB. I use AB there. So now I have this. Okay, connected to this. Let me say this is what I call Y. I call the E naught. I call this one. So I want to determine the EMF of X here. I don't know it. I want to determine the EMF. And don't forget I said E, either V or E, voltage, very last length, meaning that V1 over L1 is equal to V2 over L2 over L2. Now, AB equivalent to E naught, total voltage is same as AB. This AY here equivalent to EX. So that's it. Are we together?
Yes.
So now if I put anyone, if you like, I can say this is my V1, this is my V2. It doesn't follow. If I want to take as V1, so if I want to take as okay, if I want to take the old this as my point one, then the old this as point two. So that's all. So if I'm using V1 as E naught, that means L1. That also give me AB, EX. What is the leg two? AY. So I can look for EX now by saying E naught bracket AY over AB. So That's what I have here. So just know how to write the formula like this. So that's what I have. I have this one here. So you can see now. I think it's okay.
Yes, sir.
Okay. Now, when there is no, it can also be note these points when there is no current. So the cell is not expected to be what? It's having the same EMF. Now you are investigating. You want to. I want to find the EMF of this one. When this pointer does not deflect, this one does not deflect. You know, when it deflects, it's straight like this. That means there is no current. That's the balance point. It means that at that balance point means that the value of the EMF here equals to the value of this one here. So that's all.
Yes.
That's all compare. That's the language of, if you look, that language of comparing. You are comparing. You will know EMF of this. Let's say this one is 2.54. You have known it. You'll be using this one to strike these points, this jockey along this point until this one will not deflect. That's how it works in the practical section. You will use your this jockey to make any contact along this length. Can you hear me?
Yes, sir.
When this pointer straight like this, if it bends, you will stop. You will not stop until it is straight like this. So when it is straight like this, it's actually making contact. So at that point, so it said potentiometer is said to be balanced. It's said to be no, no deflection. If this one does not deflect, means that the value, whatever value you have here, is equivalent to this. So that's how it was. Whatever value we have is equivalent to this particular one. So it can also be in this form of the same thing, just like this one correspond to this one correspond to distance from here to here. While yeah, distance from so why this also this one correspond to distance from here to here. So that's what I'm having. So it can be that form. It can also be in this form. It's the same thing. Now, do you understand the Kirchhoff's law? This Kirchhoff's law, first, second law. Okay, I pick this thing. Okay. Okay. Let me quickly just go over this Kirchhoff's law. There are two laws, two first Kirchhoff's law. There's something called first law and second law. First law is saying that some of the current entry must equal to some of the current leaving the point. If you look at it now, I1 is entry, I2 is coming out. If you look at it, I1 is entry. Two of them are coming out. You can see the arrow. So I1 is equal to this plus this. For this one correspond to this one correspond to this. So some of the current entry is equal to some of the current leaving the point. And the Kirchhoff first law is a conservation of charge. Take note.
Yes.
Conservation of charge. And that's Kirchhoff first law. Expression of charge. Yeah, it's here. So that's the first law. Second law means conservation of energy. That's second law. Energy. Second law. So what does second law say? Second law says that some of the EMFs around a loop in the circuit is equal to some of the PDs around the same loop. Some of the PD around the same loop. Equal to some of the PD around the same loop. Now, how does it work? I have some notes here to explain how it works. To explain how it works. So if you have positive terminal of a cell is connected to negative terminal of a cell, then the EMF are added together. What am I mean by negative terminal of a cell? You have this. You know the longer one is positive, shorter one is
Yes.
negative. Okay.
Yes.
You have EMF like this, EMF like this. So if you are looking for EMF total, you add up together. So that was 2E. Add up. So that what I mean by this statement. As long as you have negative to positive. But if you now have this kind of scenario, you can see now negative to negative. You are going to subtract the EMF. That's what it's saying. You subtract. Either positive to positive or negative to negative, you subtract the EMF. So that's all. So that's all they say. Now, this point here, PD is positive. The PD is positive when transposing in the direction of the current. So I need to understand P is positive when transposing in the direction of current. Then PD is negative when transposing opposite direction to the current. What I mean by these 2 points here, this is an example of Kirchhoff's law. See the way I want to move. I want to move like that. I want to start from this point. And I want to move like this. This is where I want to move. When you see, look at this, I'll say PD is positive when moving in the direction of current. Now, if I want to move, see the way I'm moving like this. I'm moving like this. Current is also, I'm moving now. I'm moving downwards. Current is also downward. That means I'm going to have positive. PD is positive. That will give me IR. So this is what you have here. For the okay, first of all, do this one. This is what you have here. This for this one. I1. Why is it positive? Because I am moving down. Current arrow is also down. I'm moving in the same direction. That's what this question is saying. That's what this one is saying. Positive. It is positive. You can see this one. Now let me continue moving. When I get to this one, I am moving down. Current is moving what?
Up.
Up. That means we're in opposite. That means it's going to
It's
be negative.
negative.
You can see now. That's why it's in minus this. If you follow this same thing here, moving on, I am moving up, current is moving down, that's negative. Here, I am moving up, current is moving up, that's what positive. You can see now. So that's now. So for the EMF of this one, let's look at it. Why I say positive and negative? EMF say when they're positive to positive, positive to negative, they must be plus. So look at this one. This is positive. Look at this one negative. So that means this and this will be added together. That will be E1, E1, that will be E1 plus E2 because that. But you look at this one now. Look at this particular one. Look at E1. If you consider E1 and E3, you can see negative, negative. What am I going to do? It's going to be minus. Or if you also consider this and this, you can see positive, positive. What am I going to do? Minus. So that's why you have minus here, E3. So if you look at the statement here, if you look at it here, if you look at this one, these two together, so that will have negative and this. So that's how Kirchhoff's law. You now equate them together. That's called Kirchhoff's law. Now, if you're able to go through this, how to prove a series and parallel. But let me explain some important point here. This particular point here for we do. Now, okay, I've said it here. When resistance increases, current decreases, voltage increases. So whatever happens to resistance happens to voltage. When resistance decreases, current will increase, voltage will decrease. Now, from here, from this particular point, from this particular one, we have this got to this. So I want to have this terminal PDEMF. I want to plot a graph of V against I. Plotting a graph of V against I. That will be the gradient. Gradient is going to give me negative. Or if I write it proper like this, that will give me minus R. This is I. So that will give me plus E. So if you compare with this is equal to MS plus C. So if you compare now, I think you know what it means. So this means equivalent to this. That's the gradient. So if you plot, so take note of this because you see question like this. So when you have V terminal PD against current, so what do you see there? The gradient is what? Negative of internal resistance. Don't forget to, because the writer has to state the negative represent or what the negative of the graph represent. It represents what? Negative of internal resistance. When you have I to be 0 from here, yeah, if you put I to be 0 here from this particular formula here,
Yes.
Yeah. If you put I to be 0 here, let's say I to be 0. So what I
It
want to V? V is equal to what?
E.
E, thank you. So V is equal to that was here now. You can see now. So when I is equal to 0, the intercept on V axis is called EMF. So at this point, that is called EMF of the cell when current is 0. So this is the EMF of the cell when current is 0. That will be EMF of the cell. Fine. So take note of this. So let me quickly show you. So that was that on that. But let me just see. Let me just spend a little more minutes. I have things to do. So let me show you a question here so that you understand the beauty of this thing. Oh,
Yes.
before I remember something. So when you have this, you can have a set of cells like this. A set of resistor like this. Now, let me say I have my R1 here, R2, R3, my R4. And I have, so the question say they just join it together here. Either they join it together, but let me say we join it together. A, B. The question says calculate V across AB. How do we do it when you have this type? V across AB. So very simple. So V across AB can be done in two ways. You can use let me say this and this. It can be this is going to give me V1, V2, V3. You calculate, you have to go and calculate V1, let's say V1, or don't let me write some. It can be done in two ways, making use of R1 and R2. You are making use of this. So in this case, V across AB here is either V across 1 minus V across 2 or V across 2 minus V across 1. What meaning? Higher minus lowest. So higher minus, so you have to go and calculate voltage across this. V across, let me call the V1 here. Let me call it V2. V across 3, V across 4. So you can make use of this one or this, or you can also make use across of this one. You can make across of arrow 3 and arrow 4. So meaning that V across 3 minus V across 4 or V across 4 minus V across 3. So these are the way we can calculate the voltage. Across this B. So this is the way, or these are the way we can calculate this here. So it depends on what you get the same answer.
Yes.
So let me take like 1 or 2 minutes. Let me show you a question from this. Let me look at this electricity.